Welcome back. We're talking about Faraday's and Lenz's laws. And so I've got an example here. We have a loop containing a 20 ohm light bulb, as shown in blue, and it's brought into a magnetic field, B equals 2.5 Tesla. And from the drawing, you see that the magnetic field is coming out towards us. And units are Tesla. Tesla, I'm just keeping you on your toes. Webers per square meter, same thing. And so the loop is brought into the magnetic field at a constant speed, 8 meters per second, and then the figure shows it coming in from the right going to the left. And so we're going to find the current in the light bulb, including the direction. Okay, that's pretty neat. And then we ask, for how long of a duration is the light bulb on? Meaning, how long does it have current through it? Because the idea is that eventually the loop is going to be in the magnetic field. And see these ellipses over here to the left? That means the three dots. That just means the magnetic field goes on forever. So if you brought the loop all the way in, then the flux would not be changing anymore, and so then you would have no current through the light bulb, and the light bulb would not be on. But at the very beginning, when you're bringing the loop in, the flux is increasing, and so then a change in flux means an electromotive force and current through that light bulb. All right, let's try part A. So we need to figure out what is the area of the loop that overlaps the field, because the flux through the loop is going to be related to the area that's in the field. So we need, and we're bringing it in, right? So it's going to be a function of time. And you can convince yourself that the area S is going to be, first of all, this dimension is 8 centimeters. So I'll write that as 8 times 10 to the minus 2. Now, what about the horizontal direction? And again, convince yourself of this. So we're going to take 8 meters per second, right? Because that's the rate of change in the horizontal direction times the time. So if 8 is in meters per second and t is in seconds, then 8t is in meters, and 8 times 10 to the minus 2 is also in meters. And so this little nifty equation here gives you the area S that overlaps the magnetic field in square meters, right? So again, take your time and convince yourself of that. Pause the video if you need to. Now, this is not valid for a long period of time, as we will see in part B, but at the very beginning, microseconds or maybe milliseconds, you can convince yourself, yeah, there's a little bit of overlap there, and this is the equation that gives you the amount of overlap in that horizontal direction. So now the flux, of course, the magnetic field is coming out at you. And the surface area vector is also pointing out at you, meaning they're parallel. So the flux there is just B times S, which is nice, right? And so we have 2.5 Tesla, right, times 8 times 10 to the minus 2 times 8 times T, Weber. Okay, so now we get an EMF according to Faraday's law, which is negative d psi dt. Okay, and so we just need to take the time derivative of psi. So that's easy enough, right? This is just a linear relationship with t, and it's linear because we have a constant speed. So this is just 2.5 times 8 times 10 to the minus 2 times 8, and that's in volts now. And so certainly we can calculate that if we want, but what we really want in part A is the current. And so the current then is just going to be the EMF that's induced divided by the 20 ohms of the light bulb, right? So now I dropped a negative here, by the way. So there should be a negative there, so negative 2.5 times 8 times 10 to the minus 2 times 8 divided by 20, and then we go punching away in our calculators, or clicking away perhaps, and we get 80 milliamps. Great. And I'm dropping the negative sign because the negative sign is related to the direction, which I'm going to address next in still in part A. So we know that there's 80 amps or 80 milliamps or negative 80 milliamps, but let's address the direction right now. So and here's the conceptual idea behind Lenz's law. So the mathematical idea is just to include the negative sign. Here's the conceptual idea behind Lenz's law. So as we bring in the loop, right, as the loop goes this way, then you would agree, hopefully, that the magnetic flux through the loop is increasing. So the current that's going to be generated is going to be in such a direction as to generate its own flux that opposes this increase out towards us. So if you remember the right-hand rule, if there's a current that goes this way, clockwise, then you point your thumb of your right hand towards in the direction of current, and I'm not very good here, but your fingers swing around this way, and inside the loop then you have magnetic flux that points down, right? And when you go this way, you can convince yourself again you still have magnetic flux that points down. And so that's the direction, that's the correct direction, clockwise, around this loop, because the clockwise current produces magnetic flux that goes into the page, which counters the additional flux that's coming out of the page. So we will say 80 milliamps clockwise, and so you see why I dropped the negative, because we just explained the direction anyway. It's clockwise. All right, so part B, for how long of a duration is the bulb on? So this thing here is actually only valid for a short amount of time, right? Until the entire loop is in. So how long does it take for the entire loop to be into the magnetic field? Well, this thing has a length 10 centimeters, right? So, or 10 to the minus 2 meters, right? So if I take 10 times 10 to the minus 2 meters, and if I divide it by 8 meters per second, which is the speed of that thing, this is the time then in seconds, right, for this thing to travel 10 centimeters. And so that turns out to be 12.5 milliseconds. 12.5 milliseconds. So let's try to understand now why there would be no current in the loop, and thus the bulb would not be on after 12.5 milliseconds. And I said a little bit about this in the beginning of the video. So at 12.5 milliseconds, what happens is that the loop is exactly right here, where this edge here, this lagging edge, is right on the border of no magnetic field and magnetic field. And so at this point now, after 12.5 milliseconds, if I keep moving this thing forward, to the left, then the flux through the loop is not changing, because the area is not changing, the overlapping area is not changing, and the magnetic field B is not changing. So there's no reason to believe that there would be an induced EMF. That is, the d psi dt is 0 here.